Of course, in the most general case, we would like to deal with PDFs rather than PMFs. And for this, observe the following relation. The conditional CDF of x1 given the value of x2 can be written in this way. Well, by definition, this is the probability that x1 is less than or equal to x1, parameter x1, given this event here when h goes to 0. In the continuous case, this is the best we can write to express the conditional CDF. Okay, so just apply the definition of conditional probability again, or the definition of CDF. You have limit as h goes to 0, the probability that x1 is less than or equal to parameter x1, and intersection this event here, random variable x2 is between parameter x2 and a very small shift in x2, divided by this this probability, the probability that x2 is in the vicinity of parameter x2. But this probability here, I can express using a double integral on the joint PMF, sorry, the joint PDF of x1 and x2. Here, the limits of x1 will be, well, the first component will be from minus infinity to x1, because this is my event here, x1 just less than or equal to x1. But the second event, you see, x2, parameter x2, less than random variable x2, less than or equal to parameter x2 plus h. So the integration limits will be x2 to x2 plus h. Okay? And here you will have, just for this probability, you can just write this as the PDF value of x2 times h, because this was what we derived when we talked about PDFs for single random variables. Okay, now this the integration inside here in the numerator with respect to dt2, with respect to t2, you see it's from x2 to x2 plus h. So it's the integral of a function. So whatever shape it has, it's in an infinitesimal region, h here, and h is going to 0. Okay, so instead of this integration, we can just write the function value at this point multiplied by this quantity. The error will be just this area here, which goes to 0 as h goes to 0. Therefore, in this limit, I can write, instead of this integral, I can just write this function evaluated at x2. Okay, so here I will have x2. Multiply that by this difference here, which is h. Okay, now at this point, I can cancel this h with this h. So at the limit, I have this integral from minus infinity to x1 of this joint PDF divided by PDF of x2, the marginal PDF of x2. Okay, so to obtain the joint or the conditional PDF, to obtain the conditional PDF, by definition, this is the derivative of the conditional CDF. So this is equal to this. Okay. Therefore, I have computed an expression for this joint, conditional CDF, which is here. If I differentiate it with respect to x1, I will obtain the conditional PDF given here. So when you integrate it, well, this is independent of x1. It doesn't have x1 in it, so it's just constant with respect to x1. And the integral here, with respect to x1, if you integrate it, it will be just this function evaluated at x1 with respect to t1. So just write x1 here. You get the joint PDF of x1 and x2 divided by marginal PDF of x2. Okay, so this is the general form. Let me just erase the page so you can see it better. This is the general case for two components, two-dimensional random vector. Uh, Conditional PDF of x1 given x2, you get um, joint PDF divided by the marginal PDF of the condition. And of course, we can generalize this. For instance, here, let's assume we have a joint PDF of dimension 5. If I divide this to the joint PDF of x2 and x5, evaluate that whatever these are, okay? Now here, these are known values in this formulation, and x1, x3, and x4 are still unknown parameters. But x2 and x5 in this case are known values because we know their values here. They are given. So the conditional PDF of x1, x3, and x4, given the values of x2 and x5, is this ratio. So this is the general case.